Next we see this proposition. In part 1 of this proposition, there are a number of prime ideals, Pi, and there is another ideal I which is contained in the union of these Pi's. That means I is a subset of this union. Then we have to prove that I is a subset of some single Pi for some I. And in part 2, there are a number of ideals II and there is one prime ideal P, and this time P contains this intersection. That means this intersection is the subset of P. We then have to prove that P contains some II entirely for some index I. And additionally, if P equals this intersection, then P has to be equal to some one of these IIs. So let's see the proof. We will actually prove the contrapositive of what is required in part 1. That is, we are going to prove that if I is not a subset of Pi for all i's, then I is also not a subset of the union of the Pi's. And for this we are going to use induction on n, the number of prime ideals. The case n equal to 1 of course is trivial, because if there is only one Pi, that is only one P1, then this statement and this statement are actually the same statement. So that means we have a basis for our induction. Now as our induction hypothesis, let n be greater than 1, that is the number of prime ideals is more than 1, and we assume that the claim is true for n minus 1. That means this implication is true for any n minus 1 prime ideals and some other ideal I. Now for each index I in this range, obviously if we consider all the Pi's, all the Pj's except that index I, then we have n minus 1 prime ideals. That means from the list of all the Pj's, we have removed Pi, and then we are thinking of this implication. But by the induction hypothesis, the implication is true because it's true for n minus 1, and we already have the hypothesis of the implication for our entire list of prime ideals. That means I is not a subset of all the Pi's. So obviously that also is true in particular for all the Pj's where j is not equal to I. So by the induction hypothesis, I is not a subset of the union of all the Pj's where Pi is not present. Now, so what does this give us? This gives us an element in I which will not be in this union. That is why I is not a subset of this. So we write that next and let's see what comes after that. So we write that is, there exists an element xi in I which is not in this union. That means which does not belong to Pj for all such j which are not equal to I. And note one more thing, that for each index I, one such xi has been found in I, which does not belong to the Pj's where j is not equal to I. Now if we find at least one index I for which xi is not in Pi as well, xi is already not in the other Pj's, but additionally if xi is also not in Pi, then obviously xi will not belong to the union of all the Pi's, and that's what we want, because all these xi's that we are talking about are already in I. So for some particular I, if that xi is not in the union of all the P's, then I will not be contained in the union of all the P's, which is what we want to show. But only if one such index I exists. It may not exist also. So in that case, we are done. Otherwise, for each I, xi belongs to P. Now this case has to be handled separately. So that comes next. So next part we do, next we consider a special element y, which is constructed using these xi's like this. So you can see that this is a sum where there are n number of terms. Each term is a product like this, and the ith term does not have the element xi, it's the product of the remaining xj's. The first thing we can note about this y is that obviously y belongs to I. Why? Well, note that, not going into the complexities of which xi belongs to which pi or whatever. All the xi's after all belong to I. So any such product is again in I because I is an ideal. And so the sum of such products which you see here is also in I because I is an additive subgroup of whatever ring where we are right now. So it's obvious that y belongs to I. Now we want to show, and in fact we are claiming that y is not in any pi. What goes wrong if we assume that y is in some pi? Say y belongs to pi for some I. Now if you look at this sum carefully, now our I is fixed, okay. It may look a little confusing because we are using I here as a variable, but you can think of something else, say j. There is one term, precisely one term in this sum which does not have xi for that I, which is the ith term. In the remaining terms, all of them have xi. Alright. Now what will happen? If xi is in pi, so the remaining terms where we have xi in this sum, all those products are also in pi because pi is after all an ideal, so their sum is also in pi. But that one term which does not have xi, let's not think about that, okay. So all the terms of this sum except that term which does not have xi, they belong to pi. Additionally, we are assuming that y belongs to pi. So if you subtract from y the sum of all these terms which do have xi, then that thing will also belong to pi because pi after all is an ideal, so it's a subgroup also under addition. And that implies that this term which did not have xi also has to belong to pi. But is it possible? It's actually not possible. Why? Because by our construction, no xj belongs to pi where j is not equal to I. And additionally, pi is a prime ideal. So if any such product belongs to pi, at least one of the factors in the product has to belong to pi because that's how prime ideals behave. But that is not possible here because none of these xj's belongs to pi. So we have got a contradiction, and this contradiction arises from this supposition that y belongs to pi. That is why y cannot belong to pi. So let's now write what that gives us. Okay, so y does not belong to pi, but not just that. This happens for all I. That means y is in none of the pi's, and that is why y does not belong to the union of the pi's. But y is in I, so there is at least one element in I which is not in this union. So I is not a subset of this. But that's what we wanted to show in the case where we have n number of prime ideals based on the assumption that our claim is true for n minus 1 prime ideals and that extra ideal. So this completes the induction. So that means part 1 proof is over. Now let's see part 2 proof. in part 2, the original statement is the implication that if P contains, this is not contained, but I am just simply saying, if P contains the intersection of these ideals II, then P contains at least one II entirely within itself. So that means here also, just like part 1, we are not proving the implication itself, but its contrapositive. Suppose that P does not contain any II. P doesn't contain II for all I. Then obviously no II is a subset of P, that's what it means. So each such II will have at least one element which is not there in P. That means for each I there exists an element xi in II which is not in P. Now next what we do, we take the product of those elements xi. Now you go back to the definition of the product of finitely many ideals. The elements in this product are finite sums of products like this. In particular, this product also is an element here. Actually, it is one of the generators of this product ideal. But anyway, it is there. And we also know, it's a simple fact that the product of a number of ideals is contained in their intersection. This follows directly from the definition of an ideal. So that means this element is in the intersection. That means this element is here. However, this element does not belong to the prime ideal P. Why? Because none of these xi's belongs to P and P is the prime ideal. If the product has to belong to P, at least one xi has to belong to P, because that's the definition of prime ideals. So we have found an element in this intersection which is not there in P. So the intersection is not entirely contained in P. So that way we have proved the contrapositive of the implication that is asked in part 2. That means essentially we have proved what we wanted to prove. But there is that other part also, it's not over yet. If P is equal to this, then we have to prove that P is equal to some II. So next we go for that. Accordingly, for the second part of part 2, we have taken this. This time, however, we are going to approach it directly, the way it has been given. So we assume this, P is equal to the intersection, then in particular P also contains the intersection. So by what we proved just now, P has to contain some II. However, P being the intersection of all the II's actually is itself contained in every II. In particular, P is the subset of that II also. So combining these two containments, we get equality. So that's what we wanted. So that completes the proof. And next week in commutative algebra, we are going to see the notion of quotient of two ideals, and we will also see what we mean by annihilator and radical. So let me just end the video here itself. See you tomorrow with something new. Until then, this is me, Lucifer from a mathematical group. Have a nice day.